begin for today. Again, I so appreciate all of you coming. I appreciate those of you who have been faithful attending and attending when you can. It's awesome. It really warms my heart, so to speak. Okay, so here we have the warm-up problem. A 3.0, positive 3.0 Coulomb point charge is in a region of space by itself. And let's just walk through these problems one at a time. Number one, draw the electric field that this source charge creates. So remember, electric field is what we use, the electric field line is what we use to represent what would happen or what that source charge is doing to the space around it. So for example, if I brought a test charge, represented by this red dot right here, in what direction would a positive test charge feel a force from the source charge? Well, we know it would be repelled or pushed away, so we would draw an arrow like that, and that arrow would extend back to the source charge, so that would be one field line we could draw. Similarly, if I had an electric field line, or excuse me, a positive test charge down here, it would feel a force in that direction. And so we can draw the field line right there, and similarly there, and similarly up here. The number of field lines you draw is somewhat arbitrary. This is more of a qualitative representation than a quantitative one. Sometimes students draw another 4 field lines in between the ones that I've drawn already. That's totally fine. If I give you a series of field lines to draw on different charges of different magnitude, at that point I would expect you to be able to, comparatively speaking, draw field lines that would make sense, that would be consistent from one drawing to another. But again, this is a qualitative understanding for number one. Okay, number two says a test charge of magnitude positive 4.0 microcoulombs is brought into a spot so that it feels an electric force of 12 newtons from the field created by the source charge. Determine the electric field strength at the spot of the test charge. Oh, there it goes. Look, lo and behold, in case you missed it. Ooh, there you go. Test charge comes right in there. So the question is, determine the electric field strength. Okay, electric field strength. If you recall, we have an equation that says the electric field strength is equal to the force per unit charge. Okay, so in this case, the force, we're given the force as 12 newtons that test charge is feeling at that point in space. And we know that the test charge is 4.0 microcoulombs. So micro is 10 to the negative 6. So that's 4.0 times 10 to the negative 6 coulombs. So it looks like that. So a little simple math, 12 divided by 4, that's 3. 10 to the negative 6, when it's flipped up on the numerator, would be 10 to the positive 6. And this is newtons per coulomb. So the electric field strength at that spot where that test charge is 3.0 times 10 to the 6th newtons per coulomb. By the way, as usual, if you have questions, comments, please feel free to put them in the chat. I monitor it periodically, and I can try and address it as best I can. So that's the answer to number 2. The electric field strength at this particular point is 3.0 times 10 to the 6th newtons per coulomb. Notice if I was talking about a different point, say here, it'd be a different electric field strength. So keep that in mind. Number 3, draw the direction that the test charge feels a force. Well, this test charge is a positive test charge, and so we know it's going to feel a force, a repulsive force, away from the positive source charge. So something like so. Okay, so this is my answer to number 2. Here's my answer to number 3. This is my answer to number 1. Just make sure we know. Okay, number 4. Number 4 says, how would your answers to 2 and 3 change if the test charge had the same magnitude but was negative? Okay, so the electric field strength, by the way, remember, is determined only by the source charge. So 2 does not change just because I have a different test charge. Okay, the electric field strength is still going to be 3 times 10 to the 6 newtons per coulomb at that spot. Okay, E field depends on source charge. Only. Okay, so answer number 3, if it's a negative test charge, how is the answer number 3 going to change? Well, remember, if it's a negative test charge, then it's going to be drawn to that positive source charge. So the direction of the force would be opposite. Okay, so instead of being pushed away from the positive source charge, that negative test charge is going to be drawn towards it. Okay, awesome. So again, keep asking questions. If you still have questions about the warm-up, go ahead and write them in the chat box. I'm going to continue forth, but I can double back if need be. Okay, let's talk about today. I want to talk about guest speakers. I want to talk about flex and homework. We're going to talk about electric field and electric potential, and you will get time in the breakout rooms. Okay, 2 guest speakers this week. Robbie Gottesman, really interesting person, data scientist, so to speak, undergraduate physics major from Reed College. You can see he's done quite a lot of different things. He will be talking tomorrow at 1 o'clock. Strongly encourage you to attend. And then Greta Binford on Thursday, Spider Woman. Wow, Oregon Professor of the Year. Sounds awesome. So strongly encourage you to attend her talk as well. When am I available this week? By the way, I'm thinking of changing this all-class flex, so stay tuned. I don't want it to basically coincide with Greta Binford's lecture. So anyway, right now it's 1 to 2, but just note that I might be sending a reminder out adjusting that time. And you please know that I'm always available via remind and email, which some of you have been very good about following up with me. I just want to emphasize again, so love what you are doing, all of you who are showing up routinely or when you can. You know, anything you can do to continue your learning and stuff is so important for all these different reasons. And probably the least important of them at this point, obviously, is some sort of grade for this semester. But many, many important things about what you're doing here. So kudos to you. Keep up the good work. And I have a joke in a little while for you, so just be waiting for that. The homework for this week. One problem set that you're going to get, it's going to go live on Google Classroom within the hour, I believe. And it's going to be due Monday evening. It's a set of 6 problems, I think, 6 or 7. All right, here we go. 3 learning targets for today. I can apply electric field concepts and relate them to electric force in situations. The second, I can describe how electric potential energy, electric potential, and work are related. And the third, I can apply the principles of electric field and electric potential to solve problems. And the fourth is I can laugh heartily at Mr. Bob's jokes. All right, let's go. If you are watching a replay of this video and you did not watch the Bozeman Science electric force video that I have put on the blog, please pause this video, go watch it. It's about 6 minutes, and I think it's really worth your while. Let's continue forth, though. So there are some key things that I want to talk about in terms of electric field drawings. And so this is important because these are things that I've learned over the years are difficult for students to comprehend, things students sometimes get mistaken about. So it would be a good idea to jot notes down or at least make mental notes as you see fit. So on the left there, this first drawing that you see here on the left is the electric field lines that surround what we call a dipole, an electric dipole. An electric dipole really simply is a positive charge and a negative charge of equal magnitude separated by a small distance. So notice, you can see there, it's quite a beautiful electric field sort of pattern that you get. The key idea I want to offer to you here, and this is why I've shown you this field drawing, is because let's say I have a spot here, this purple dot. If I bring a test charge, say a positive test charge to that spot, in what direction is it going to feel a force? Well, the key idea here is it feels a force in a direction that is tangent to the field line at that point. So it's going to feel a force in a direction like so. And similarly, let's say I picked a spot over here, another purple dot up here on the left. Again, if I want to figure out what direction will that test charge feel an electric force, I'm going to draw a line that is tangent to the field line at that point. So the key idea here is this, is that if a field line is curved, then tangent to that field line is the field vector, meaning that's the direction that a test charge will feel an electric force if it is placed there. Okay? A positive test charge in this case. And we know that a negative test charge would feel a force in the exact opposite 180-degree direction. So that's one key point I want you to keep in mind as you look at these field drawings. And that's also going to be important for the electric field hockey game you're going to play later today. The second key point is this. Take a look at that middle drawing, and I'm going to draw a box around this red dot here. Notice I've got this red dot, and I'm just going to draw a box about this size. I'm going to draw a similar sized box around the blue dot way out here. Take a moment, count the number of field lines that pass through those boxes. So for the red dot there, I count 1, 2, 3, 4 field lines that somehow penetrate that box. What about for the blue dot? Only 1 field line, okay? And so what we can say here is an important note, that the density of electric field lines, how close they are together, gives you a qualitative sense of how strong the electric field is. So just based on those boxes that I drew and counting the lines and looking at the electric field line density, I can conclude that the electric field strength around the red dot is much significantly bigger, higher, than it is around the blue box. So where the field lines are closer together, the electric field strength is greater. And that gets to this idea of field line density, number of field lines per unit area or unit volume. Okay, third point that I want to make. Look at this drawing on the right. Assume this drawing is 2 plates, and these plates are really long, much longer than you see here. I've kind of just given you a cutout, but these plates extend up and down beyond the slide, and they're really close together. And notice there's 2 dots there, a green dot and a blue dot and a yellow dot. And again, I'm going to do a similar thing where I'm going to take a box of similar size and draw it around each of the dots. And similarly, I'm going to count the field lines that penetrate the boxes. And notice in this case, I have the same number of field lines that penetrate both boxes. So the electric field line density is very similar or the same. This is kind of a corollary to the last point. If you have a region where the field line density is constant, that means the electric field is constant in that region. And that means the force felt by the test charge is also constant. So notice the electric field strength at the green dot is the same as the electric field strength at the yellow dot. And it's pretty much the same electric field strength at all points in that region, because if you look at it, the field line density doesn't change. And this is a very common setup, 2 parallel plates close together, positive charge on the left side, negative charge on the right. You're going to spend a lot more time learning about these. Certainly a little bit more time this year, and certainly a lot more time for those of you who go on to HL Physics. The last point I want to make is this. When you are looking at drawing your field line drawings, because sometimes you will have to draw field lines cannot cross. So for example, let's just say that I were to draw a field line like so. Let's say there was another field line in here that I drew like this. Okay? This is not an acceptable sort of field line drawing. And the reason is because I can't have field lines crossing, because notice, let's take a look at this green dot right here. The question I would ask is if this field line drawing, this additional one, is valid, then where is the electric field going to push this test charge here if I put it at the green dot? We don't know, because it's actually feeling, the electric field, the net electric field is shown as occurring in 2 directions simultaneously, and that just can't be, okay? So keep that in mind, okay? When we're talking about net electric field drawings, you can't have field lines that cross, okay? So I'm just going to erase that because I don't want to even give you the impression that that's okay. No, don't do that. Uh-oh. Hold on. Here we go. All right. There we go. It's gone. Awesome. All right, here we go. Now, I really need you to put your thinking caps on, like my 3rd grade teacher, Mrs. Moskowitz, used to say. So, I'm going to walk us through a couple of scenarios here. And with each scenario, I'm going to start with something that hopefully we're very familiar with, and I'm going to use the analogy and extend it to something we're not familiar with and is more abstract. So let's start with here on the left. This concept of potential energy. If I have this textbook in my hand, and I take that textbook and I lift it. I lift it 1/2 meter, as you can see in the drawing there. I've exerted a force on that textbook. I've caused it to move in a certain direction, force, direction, displacement. What can we say I've done on the textbook? I've done some work on the textbook. And in doing work on the textbook, what have I done? I've changed the energy in the textbook. In this case specifically, I have changed the amount of potential energy, gravitational potential energy the textbook has. The textbook, at the end of this process, has more gravitational potential energy because of the work that my hand has done on it. Okay? Good. Let's look at this middle scenario. In the top picture there, I have a coiled spring. And let's say that coiled spring is basically undisturbed. Okay? It's at its natural equilibrium position. Potential energy, no Hooke's law force on it. Then I take my hand and I push it to the right, and I compress that spring. Similarly, I am exerting a force on that coiled spring, displacing it a certain amount, force, displacement. That means my hand is doing work. And in this case, when I do work on that coiled spring, I change the energy of that spring. And we've talked about this. This is a specific type of potential energy, which we call elastic potential energy. So in doing so, in both of these cases, what have I done? The work done increases the potential energy of each system. So for both these cases, we can say work done equals the change in potential energy. And if I wanted to use the abbreviations that we've used throughout this year, W stands for work, equals, triangle stands for change in, E stands for energy, lowercase p is potential. Work equals change in potential energy. And just need to know whether it's gravitational or elastic, but it's pretty much the same principle operating here. All right, we good? All right, you ready for this? Let's do it. Notice in this drawing, I have a bunch of source charges on the right-hand side. And then on the left, there is this test charge, small q. You can see my hand is on it. And then similar to what I did with the coiled spring, I'm gonna push that positive test charge closer to those positive source charges. What do I have to do? I'm exerting a force on that test charge, displacing it a certain distance. Force, displacement. I am doing work on that test charge. And when I do work on that test charge, I have to change the energy. I am changing the energy of that test charge. Okay? And the energy that I'm changing in this case is something we call the electric potential energy. It's the same idea as the elastic potential energy scenario and the gravitation potential energy scenario. Same idea. It's just more abstract. We're now talking about charges instead of books and gravity fields and coiled springs. Okay? I want you to keep this in mind because this topic can get really confusing, but I have found that students and I myself find it helpful to keep these analogies in mind as we proceed through a lot of these different scenarios. Okay? So always try and keep this in mind. And this applies to the right-hand scenario. The work done equals the change in potential energy. W equals triangle EP. Okay. If you hear my dog in the background, it's because we have a bird feeder on the porch and these squirrels have been going crazy over it, and the dog goes crazy every time it sees a squirrel on the porch. Anyway, try and ignore it if you can. All right, so if you look here on the next slide, you can see that there is the same drawing that I had last time, but I just added the fact that there's low potential energy for that positive test charge at the start of this process, and at the end, it has a higher potential energy. So if I were to ask, if I were to calculate the electric potential energy of the source charge, okay, excuse me, of the test charge, or any set of charges, one way of thinking about it is this, that the electric potential energy of a set of charges is the amount of work that must be done to assemble a set of charged particles. So think about these charged particles starting infinitely far away from each other, and we have to do a certain amount of work to get one positive test charge, or one positive charge closer to another positive charge. Okay? But remember, with gravitational potential energy, we rarely, I think I've emphasized this somewhat, it's not so important to say what is the actual gravitational potential energy at a certain point, because that's kind of arbitrary depending on what you set your zero reference level to be. The more important topic, the more important quantity to remember, to keep in mind, is how is the change in potential energy, the change in gravitational potential energy between 2 points in a region. And the same goes for electric potential energy. If I want to talk about the change in electric potential energy, that's going to be the amount of work that must be done to move a charged particle between 2 specific points in a system. And I would say, in this case, a better way of saying that is in an electric field. So there's an electric field of some sort set up by a set of source charges. And so the change in electric potential energy of a test charge within that field is the amount of work that must be done to move a charged particle between 2 specific points within that field. Okay. So let's keep this in mind because we're going to develop this concept even further. But first, you ready for the joke? All right, make sure you get ready to unmute your microphone for a couple seconds to laugh heartily. Here we go. I like this one. What did Cinderella say when her mail order photos did not arrive? What did she say? Someday my prince will come. Very good, very good. I like that joke. Okay. Let's continue developing these concepts, and we're going to go a little further. We're going to talk about something called potential difference and electric potential. So here we go. Here's the setup. I have a positive source charge, capital Q there. I have a smaller test charge, lowercase q. And lowercase q is starting at some point A in that electric field, and it's being moved from A to B. Okay? So we have 2 definitions we can talk about here. The first one is something we call electric potential difference. By the way, electric potential gets the abbreviation capital V with a lowercase e. Okay? Electric potential difference just then gets the abbreviation triangle VE because the triangle means difference, change it. So the electric potential difference between 2 points is the amount of work done per unit charge in moving a point charge from A to B. Okay? The amount of work done per unit charge in moving a point charge from A to B. You can also think of it as the electric potential energy per unit charge in moving a point charge from A to B. Okay? So a couple of equations I want to talk about here. First of all, this top one on the left. Notice here it says VE equals EP over Q. This VE, remember, is electric potential. Electric potential. The EP is the electric potential energy. And that's in joules. And the Q is the charge in coulombs. And then down here I have very similar looking equation, but slightly different, whereas triangle VE, meaning electric potential difference or change in electric potential, equals W. W is work divided by charge, or the change in electric potential energy per unit charge. Let me offer a quick analogy that might be helpful. It seems to have helped students sometimes in the past. Hold on one second. Okay, so here's the analogy. If I go to the store and I want to buy apples, okay? So one day I might go to the store and I might buy 1 pound of apples. And if apples are $2 a pound, the cost, the amount of work required for me to buy those apples is going to be $2. But if the next day I have to go and buy 2 pounds of apples, and the cost is still $2 per pound, then it's going to be 2 times 2 or $4. So you can think about the electric potential energy as the total cost that I paid. One day I paid $2, the next day I paid $4. But the electric potential or the potential difference can be thought of as being the cost of apples per pound. So it's always $2 per pound. Let's say, for example, moving from A to B, and it's just a question of how many pounds of apples you're buying or the amount of charge that you're moving. Okay, that may be one way that could help you. Think of it as a cost per unit charge or per unit apple, right? Electric potential difference. Electric potential is the work or the electric potential energy per unit charge. A couple more things to help you kind of understand this and put it into context. The units on electric potential and change in electric potential or potential difference is joules per coulomb, right? Work is in joules, the potential energy is in joules, Q is coulombs, charge in coulombs. Joules per coulomb is more commonly known as a volt, and it gets the abbreviation capital V. We all have heard of volts, right? 9-volt battery, etc. We use that fairly common in our daily existence, okay? So I want you to think about this, that when we get to circuits, which we're going to talk about next week, we're going to often use the term voltage. And please, please, one of the things you want to think about, always have in the back of your head, is that voltage is the same thing as potential difference, okay? And voltage is the same thing as potential difference, delta VE. And I'm going to try and remind you of that along the way as well. Okay, if you understood everything in this past slide, then I would be shocked. So again, if you're a little discomforted by what you're seeing right now, don't worry. We're going to get some practice with this. All right, so let's actually get some practice with it right now. Here's a sample problem. On the right there, I have a bunch of source charge. On the left, I have a positive 2 coulomb charge at point A. And I am going to take that positive 2 coulomb charge from point A to point B. Notice I'm told that the electric potential energy of a 2 coulomb charge at A is 6 joules. Okay? Notice also it shows me down there below that when I move from A to B, the positive 2 coulomb charge, I do work in the amount of 4 joules. Okay? So I'm going to use all this information to figure out answers to a couple questions. First question is, what is the change in potential energy when moving the charge from A to B? Okay? Well, remember, what did we just learn? The change in potential energy is equal to the work done. And so that would just be the 4 joules that you see there. That's the amount of work done in moving those 2 coulombs from A to B. The second question is, what is the potential energy of the charge at B? Okay, well, the potential energy at B is just simply going to be the potential energy at A plus whatever the change in potential energy was. And that's going to be equal to 6 joules, what we started with. We said we added 4 joules of work to it. So at B, we have 10 joules. Okay? Number 3. Number 3 is a bit more challenging. The question is, what is the electric potential at points A and B? Okay, if we recall, let's go back. What is electric potential? Electric potential is equal to the potential energy per charge. So the electric potential at point A is going to be the potential energy at A divided by its charge. So that's going to be, we know that's 6 joules divided by 2 coulombs, or 3 joules per coulomb, which is also equal to 3 volts. So we can say the electric potential at point A is 3 volts. All right. Just pause there for a second. Again, let me just check the chat box, see if... Similarly, at B, at spot B, we can say the same thing. The electric potential at B is equal to the electric potential energy at B divided by the charge at B. We know that B has 10 joules of electric potential energy divided by 2 coulombs. So that is 5 joules per coulomb, or 5 volts. So notice what we've done. We've gone from this idea of electric potential energy and work, and we have, what can I say? Standardized is maybe not quite the right word, but ratioed it, so we now can just talk about the electric potential at each of those spots. 3 volts at A, and it's 5 volts at B. Okay, so here's what I want to do. I want to give you another sample problem, similar to this one, very similar. I want to give you about half a minute to see how far you can get on it, just working on it individually, and then I will give you, we'll walk through it together, just walk through the answers together. But I think it's important here that you spend a little time with this. So here we go. There is the problem. I'm going to give you about a minute to work on it. This would also be a good time if you've been troubled, had a question that you haven't been quite able to ask from previous slides. You can type it in the chat box now. I'll take a look at them as well. But take about half a minute here, half a minute to a minute to see how far you can get on this. This is quite similar to the last question. I did add question 4 there. So let's do it. Okay, I suspect some of you haven't had enough time, but in the interest of making sure you have time in the breakout rooms, I'm going to reveal the answers and I will talk through them here as well. So question 1, what is the change in potential energy when moving the charge from A to B? So again, remember the work is equal to the change in potential energy. So it's going to be 9 joules because that's what shows down here. 9 joules is given to you there. The second question, what is the potential energy of the charge at B? Well, that's just simply the initial potential energy it had at A plus the change. So we know it had 12 joules at point A. We added 9 joules to it. So it has a total of 21 joules at point B. Question 3, what is the electric potential at points A and B? So similar to what we did last slide, we're going to take that equation. Electric potential is the electric potential energy per unit charge. So at A, it's 12 joules divided by 3 coulombs, which means 4 joules per coulomb, or 4 volts. Similarly, at B, it is the electric potential energy at B, which is 21 joules divided by the same 3 coulombs, or 7 joules per coulomb, or 7 volts. Finally, question 4, what is the potential difference between points A and B? So potential difference between 2 points is equal to the potential at B, the final point, minus the potential at A, which is the initial point. So you would just take your answers to question 3, 7 volts and 4 volts, subtract them from each other, and you would get that potential difference, which is 3 volts. And to just put a finer point on it, that means anytime I move a charge from A to B, if I move a 1 coulomb charge from A to B, I'm going to have to do 3 joules of work. A 2 coulomb charge is going to be 3 joules per coulomb, or 6 joules of work. A 3 coulomb charge, like you see here in the problem, is going to require 9 joules of work. A 4 coulomb charge would require 12 joules of work, et cetera, et cetera. Okay, again, I just want to emphasize, if you are struggling a little bit, I'm a little uneasy about what we're talking about here, don't worry, you're in good company. You will get more practice with this. So, a couple more slides and then you've got breakout rooms. What unit of energy have we been using so far this year? By far, the most common unit of energy is the joule, okay? But when dealing with atomic particles like electrons and protons, there's a more convenient way to measure energy, and scientists, physicists do this sometimes. And then the electron volt is equal to 1.60 times 10 to the negative 19th joules. And no, we don't use calories. I think that's what you said, Roman. No. So, and the abbreviation is 1 lowercase e capital V equals 1.60 times 10 to the negative 19th joules. Some of you are probably wondering, this seems kind of arbitrary, Mr. Bob. Why did they choose that? Well, there is a method to the madness. And I'm going to give you a statement here that you're going to want to probably jot down or record because it'll come in very handy in one of the homework problems and in certain situations. 1 electron volt is the amount of kinetic energy an electron gains when it's accelerated through a potential difference of 1 volt. I'll say it one more time. An electron volt is the amount of kinetic energy an electron gains when it's accelerated through a potential difference of 1 volt. That can come in very, very handy. Okay. One more sample problem I want to walk you through, just so you get a sense of how to do one of the in-class problems I'm going to have you do. Here it is. So notice there's 3 scenarios here, A, B, and C. In each of these scenarios, I have 2 source charges. The source charges are in red. And I'm asking you to determine the net electric field at the blue dot in each scenario. And I'm asking you to rank the magnitude of that net electric field against each other. So which of the scenarios has the greatest net electric field magnitude at the blue dot, and which one has the smallest? So remember, electric field is a vector, okay? So electric field is a vector. So we can do vector sum, vector addition, just like we do with other vectors, force vectors, you name it. So, and that's what we're going to do here. So notice the way to approach this problem is to say, okay, the electric field, remember the electric field from a point charge is equal to KQ over R squared. Okay, so just keep that in mind. So if I were to draw, if I'm going to call this charge 1 and charge 2, the electric field contribution from charge 1 at this blue dot, well, that's going to have, that electric field is going to look something like this, right? It's going to be, a blue test charge is going to be pushed away from that charge. But similarly, that source charge underneath is going to, that's not what I meant, create an electric field in that direction. Okay, and because I said these charges are the same size and they're equidistant from each other and from the blue dot, so to speak, in this case, the net electric field is going to be what? 0, because the field vectors are going to cancel each other out. Meaning a positive test charge placed there is going to feel no net force in that field, and that makes sense because the 2 positive charges are equally drawing it towards it, so the net effect is nothing. Okay, what about this middle one? Let's see, this is a negative source charge. So the one that's, I'm going to call this 1 and this 2. So from 1, it's closer, so it's going to feel a pretty strong electric field from source charge 1, drawing it towards it, right? Source charge 2, it's also going to be drawn towards it, but not as strongly because it's further away, right? So if it's further away, the electric field strength is smaller. So this would be E2. Okay? And so then to add these together, E1, E2, let me do that in a different color. If I can get this to come up. Come on. Maybe not. Oh, there we go. So E net is something like that, right? This is qualitative, right? We're doing here. Finally, in part C, what do we got here? Let's call this 1 and this 2. So the contribution from 1, it's further away. It's drawing the blue test charge towards it. So it might look something like this. An E field vector looks like this. And then charge 2, that source charge is going to push it away, and it's going to push it away significantly. Okay, because it's closer. So it might look something like so. So when I go ahead and draw this here, this is E2. This is E1. And so my E net is going to maybe look something like this. Okay. And I drew those bigger than the other one, but you get the idea. So when I go rank the overall magnitude of the electric field strength at that blue dot, okay, the biggest net electric field is going to be at B, right? The smallest is going to be at A, and C is going to be between the 2 of them. So that's how you could attack a problem like that. Okay. If you have questions about that or anything, please go ahead and put them in the chat box. What I'm about to do here is give you your breakout room instructions and send you to your breakout rooms. I recognize that Some of you may not be able to stay much past 11:10, which is totally fine. Whenever you need to leave, please go ahead and leave. So in the breakout rooms, what you're going to do is you're going to do two things. You're going to create and share a Jamboard, because what I want you to do is there are these in-class problems. The in-class problems are located on the blog, okay? These are on the blog. They're there right now. Copy these numbers down because I don't want you to do all of them. I just want you to do these select numbers: 1, 3A and B, 4A, 5, 6, and 7. So spend about roughly 15 minutes working together as a group on your Jamboard, doing those problems. And then once you're done with that, there's a game on Physics Classroom that I've given you a link to, again, on the blog, called, I call it Electric Field Hockey. I think it actually has a different name, but just click on it. And the goal there is to basically create a net electric field that you're able to take a test charge and move it around these obstacles and into a goal, so to speak. It's really fun. I think it's really fun. So you can play as much or as little of that as you want. Some students spend a lot of time with it. Some students are done with it after 10 minutes. And again, as usual, if you feel like you have to leave for whatever reason, feel free to leave as you need to. So there's the breakout room link. So this concludes the big meeting, so to speak. As usual, you can stay behind if you have a question. I will stay on this call for about another minute or two as you proceed to your breakout rooms. Thanks, everyone.